Welcome back to Machine Design course. In this video, we'll talk about fatigue failure theories. Introduction to fatigue failure theories. Most failures in machineries are due to time-varying loads rather than to static loads. These failures typically occur at stress levels significantly lower than yield strengths of the material. Thus, using only the static failure theories of the last chapter can lead to unsafe designs when loads are dynamics. So in previous videos and chapter, we developed theories particularly for static loads. But we know that most machineries are under dynamic loads, so we need to have a separate type of failure theories for these type of loads. Okay, so in this video, you could see different type of dynamic loads. It could be a fully reserved sinusoidal load. Okay, so what is this type of loads? Basically, it's just a pure sinusoidal load that goes from 0 to maximum and minimum, and the mean value here is 0. Okay, we have repeated time varying loads are those that are sinusoidal, but the minimum is 0. Okay, and is shifted equal to the amplitude of the sinusoidal. And we have fluctuating loads are those that both maximum and minimum values are either in the positive or negative territory. So we will discuss the effect of these loads later on the theories and how we should consider the effect of the mean value and the amplitude of the dynamic loads later in our theories. Okay, so the graph you could see here is Wöhler strength life or SN diagram. We will discuss in the coming slides where this graph comes from and how we could develop this graph either experimentally or theoretically, and how we could interpret this graph. But quickly, we could see that here we have fatigue failure, fatigue strengths, okay, fatigue strengths, okay, is S, and here we have number of cycles. It's a number of cycles that our part goes under. For example, when we have a beam or rotating beam, let's say, that beam could be stationary or static, so we have 0 cycle, and then we will be on this vertical line, and you see that the strength of the material is equal to the ultimate tensile strength because the load is static. Or we could rotate that beam for 10 cycle, 100 cycle, 1000 cycles, so on and so forth, and we see that the strength of the material drops here. Okay, so it's not yet equal to ultimate tensile strength. It will be lower than the static strength. Okay, here you could see that some material will show endurance limit, and we will discuss this endurance limit. It means that by increasing the number of cycles, the strength of the material does not decrease anymore. Or some materials doesn't show any endurance limit, like aluminum, and the strength of the material could decrease and decrease more and more by increasing the number of cycles. You could see that this graph is logarithmic, and the number of cycles are equally distanced in the logarithmic scale. The SN or Wöhler diagram is the standard way to characterize the behavior of materials under completely reverse load and is still in use. Okay, so don't worry if you don't know yet uh, where that SN diagram comes from. We will explain completely, experimentally and theoretically in coming slides. So still we are in introduction to the topic. The mechanism of failure in fatigue was not yet understood. So in the past, they didn't know exactly why the part fails under fatigue or under these dynamic loads and rotations. And the brittle appearance of the failure surface in a ductile material caused speculation that the part had somehow become tired and embrittled from the load oscillations. So what they observed in the past, they saw that for a ductile material, when they put it under dynamic load, it behaves like a brittle material and it breaks sooner than expected, or that it shows less strength than, let's say, under static loads. So they said, okay, the material is tired of going under these repetitive cycles, and that's why they said the material is tired or fatigue. Okay, so fatigue is a synonym of tired somehow. Okay, so the name comes from this historical observation, but of course, the real mechanism of failure is not uh, fatigue with the name of tired. Okay, but still we use fatigue failure. When we say fatigue failure, we mean dynamic failure or going under dynamic loads, and of course it has its own mechanism different than static failures. Okay, mechanism of fatigue failure. So what is that real mechanism? Fatigue failure always begins at a crack. The crack may have been present in the material since its manufacture, or it may have developed over time due to cyclic straining around stress concentrations. So since it goes under stress cycles and the stress becomes positive and then negative, uh, there will be a stress cycle, and when there is a crack in the part, tips of the crack usually um, create a stress concentration, enhance the stress, and the crack basically develops and progresses forward, and the opening of the crack becomes bigger and bigger. There are three stages of fatigue failure. Crack initiation. So crack starts, crack propagation, the crack grows, and sudden fracture due to the unstable growth. Yes, and you've seen that, for example, for windshield of cars, we have first a small crack starts to grow, and then suddenly one day in the morning you come and see that, wow, the crack grows and now covers all over the windshield. Okay, and this is the same kind of mechanism that we have these three stages for the crack and in the fatigue failure. The first stage can be of short duration, the crack initiation. The second stage involves most of the life of the part, okay, so it takes more than the first and the last one. And the third stage is instantaneous. It's very quick, okay? Crack initiation stage. Ductile material develops cracks by local yielding. So why that crack develops uh, at the first stage? Because of the local yielding. Yes, there is one section of the part with the stress concentration, some notches or some displacement in the lattice of the material, and that creates some local stress concentration, and there will be a local yielding. Okay, so the stress at that point goes above ultimate tensile strengths of the material or yield strengths of the material, yield strengths for the ductile material. Brittle materials do not yield as ductile ones and will tend to develop cracks more rapidly. Why? Because brittle materials, we know that it reaches to the ultimate tensile strength quickly, and after that is failure, yes? So that's why they develop cracks quicker than a ductile material. Ductile material, they have a region of plasticity. That plasticity will basically postpone the failure or development or propagation of the crack. Ductile materials which do not yield may skip this initiation and proceed directly to crack propagation at sites of existing voids that serve as microcracks. Okay, so there are some existing voids or displacement in the lattice of the material, and that creates that's a part that we have stress concentration, and micro cracks will develop at those parts, and then we have a crack initiation. So crack will start anyway for ductile or brittle materials when we have a local yielding or stresses above ultimate tensile strengths locally. Then we have crack propagation stage. Once a micro crack is established, the mechanisms of fracture mechanics become operational. The crack grows small amount when the stress cycle to a compressive stress region to zero or to be sufficiently lower tensile stress, the crack closes. The yielding momentarily stops and the crack again becomes sharp, but now at its longer dimension. Okay, so we have this micro crack develop, then we have a cycle of stress goes from positive to negative. But when it goes to the negative and zero, we have a compressive. That compressive stress closes the crack. Okay, then we will have a sharper edges, and now we have a high stress concentration and is ready for the cycle of stress to go positive. This process continues as long as the local stress is cycling from below tensile yield to above the tensile yield at the crack tip. Thus, crack growth is due to tensile stress, and the crack grows along planes normal to maximum tensile stress. Okay, so when we are in the compressive, a crack closes, edges becomes sharper, stress concentration factor increases. Then when it goes to the positive cycle, because we have a stress concentration and the stress goes beyond the yield strength, crack again develops and then again goes to the negative cycle. So we have this positive feedback from the tip of the cracks, and the crack propagate. And finally, we have fracture. Crack will continue to grow as long as cyclical tensile stress is present. At some point, the crack size becomes large enough to raise the stress intensity factor K at the crack tip to the level of the material's fracture toughness, and sudden failure occurs instantaneously on the next tensile stress cycle. So we discussed the stress intensity factor in first chapters of material properties, and we know that when it reaches to the material's fracture toughness, then we could have a sudden failure. So the crack develops, this propagation continues until this stress intensity factor reaches to the critical level, and then at that point you have suddenly a failure or development of the crack. This failure mechanism is the same whether the condition of K is equal to Kc or stress intensity factor is equal to the critical intensity factor, was reached by reasons of the crack propagating to a sufficient size or by the nominal stress being raised sufficiently. Okay, that was briefly the mechanism of failure in uh, fatigue loads or dynamic loads. Okay, but now we know why we have this type of failures. It's because of this crack initiation, uh, propagation, and then finally crack uh, fracture. But now we want to see how we could practically develop a theory to predict fatigue failure. Okay, so let's remind you again with fatigue loads for rotating machine loading. The typical stress strain function experienced by a rotating machinery can be modeled, which shows then dramatically as sine waves. Okay, so these are the simplest way to show a stress strain function. Okay, so it could be a sinusoidal. This is basically the simplest way to show a dynamic load. It goes from positive to negative. It's by showing a sinusoidal function, and goes from positive to negative. So we have fully reverse one. The mean value is 0, and the alternating value is constant. Okay, so this is the mean value, alternating value. This is a amplitude of the sinusoidal, basically. Delta sigma is sigma maximum minus sigma minimum. We have repeated one, same sinusoidal but shifted up or down. So the the minimum value or the maximum value is 0. And we have fluctuating one, that the whole sinusoidal is either in the positive or negative territory. So the stress range delta sigma is defined as delta sigma is sigma maximum minus sigma minimum. I'm just showing you here a fully reversed one, but if you are willing to review the other ones, then study the previous slide. The alternating component, or sigma A, is found from sigma A is sigma max minus sigma mean divided by 2, and the mean component sigma M is sigma max plus sigma mean divided by 2. Two ratios can be formed: R sigma mean divided by sigma max, and A sigma A divided by sigma max, where R the stress ratio and A is the amplitude ratio. When the stress is fully reversed, figure A that we have it here, R is equal to -1 and A is infinity. And when its stress is repeated, figure B, again study the previous slide, R is 0 and A is 1. And when the maximum and minimum stresses have the same sign as in figure C, both R and A are positive, and R is between 0 and 1. Measuring fatigue failure criteria. So before developing any theories, we need to study the experimental data. What people have done empirically in the past to show the fatigue failure theory. Wöhler loaded a rotating cantilever beam in bending to achieve variation in stress with time. So there was a cantilever beam, there was a constant load at the tip of the cantilever beam, but the cantilever beam was rotating. Okay, so once we have this rotation at the specific cross section, let's say at the base, when we have maximum stresses, we have maximum bending stresses for that cantilever beam, for one specific point, as that point is rotating, it goes from the maximum positive stress to the maximum negative stress, or from the maximum tensile to the maximum compressive stress. So Wöhler basically tried to replicate that fully reversed sinusoidal dynamic load by a rotating cantilever beam. Okay, so I suggest you to pause here, think about the cantilever beam and the constant force at the tip, and think how a rotating beam could experience a fully reversed stress load. Why one specific point let's say at the cross section or at the type fiber um, at the fixed base should experience that fully reverse stress. Okay. Then R.R. Moore later adopted this technique to a simply supported rotating beam in fully reverse pure bending. Okay, so he did basically the same technique. He had a beam, but instead of a cantilever beam, he used simply supported beam. Okay, and then he rotated the beam. Okay, and he had two constant forces at the center of the beam. You could see that one point at the cross section could experience pure bending that goes from positive to the negative. Most of the available fatigue strength information, or most of those SN diagrams, is for a rotating beam in fully reverse bending. Okay, so it comes from this experiment, with less available for axial bending. We'll discuss the axial bending in coming slides. Okay, so you could either use a cantilever beam or a simply supported beam or axial loading. The axial loading is very similar to the tensile test. Okay, so you remember that universal testing machine, that UTM machine, that there was a specimen put in between the jaws of the machine, but that machine only could apply quasi-static loads. Okay, but imagine the same machine that could apply dynamic load, and that load will be axial loading. Okay, so R.R. Moore rotating beam test, fully reverse bending, a highly published specimen of a 0.3 inch diameter is mounted in a fixture which allows a constant magnitude pure bending moment to be applied while the specimen is rotating at 1725 RPM. Okay, so again, it was a simply supported beam applying that specimen with specific size based on standard into the machine, apply forces to have a pure bending and start rotating that specimen. And then for the axial test, as I said, is very similar to a UTM machine, universal testing machine, has ability to apply any combination of mean and alternating stresses. Okay, so we could replicate any of the fully reversed or repeated or fluctuating type of dynamic loads. These type of axial test needs more advanced machine at the time of the more those didn't exist. So that's why they use this type of test. But still, the experimental data from this pure bending moment are available in handbooks and the books and are widely used and published. Okay, so let's watch this video to understand better the whole topic since now, and also some coming other slides. I decided to put this video somewhere between slides to help you understand better the topic and get a better whole picture from these tests.
Fatigue test. Many everyday items are not loaded uniformly, but rather non-uniformly with periodically changing loads. This is quite obvious in off-road biking. Frames, handlebars and wheels are subjected to high alternating mechanical loads. It is just as obvious in the case of a garage door spring. The spring is unloaded when opening the door and loaded when closing the door. The connection rods of this old compressor have endured a large number of rapidly changing tensile and compressive forces. Even when cycling quite moderately in the city, many components are exposed to periodically varying loads without us being aware of it. The crank arms are alternately under load, then swing back almost load-free, are under load again with the rhythm of pedaling. The spokes, the pedals, even the individual links in the chain are stressed periodically. Also, the railway bridge over the River Rhine, seemingly totally addressed, alternately has to bear the additional burden of a heavy freight train and then only its own mass. Aircraft experience quite different stresses during take-off and in turbulence than on ground. This type of loading is generally termed fatigue loading, and the material responds to it, fatigue. The term fatigue is used because it takes some time for the failure to occur under repeated loads. The problem with materials is that they normally endure less at repeated loading than with a once-only load. The wire does not break when first bent, but bending it back and forth repeatedly leads to an early fracture. This bicycle crank arm had only been able to endure the cyclic loading for a certain time before it broke. The fate of the garage door spring was the same. It had borne the opening and closing of the garage door about 60,000 times before it finally fractured. The broken exercise equipment, a torn blade of a fan, a bandsaw blade full of cracks, the broken screw, a defective universal joint, and many other examples show how important this phenomenon is. Each day, thousands of items break due to cyclic, often repeated loading. How can we make sure that all these components withstand the cyclic loads? To achieve this, one has to test the materials appropriately. We intend to measure the fatigue strength of a frequently used steel in our laboratory. Hot-rolled steel rods made from the structural steel S235JR are used as base material. In order to eliminate the influence of the surface and to stress the material in a well-defined manner, suitable specimens have to be machined from the rods. This specimen type would be ideal. The shoulder-shaped ends have been designed for safe gripping. The actually tested region is cylindrical with a diameter of 6 millimeters. The material tester goes to the workshop to get 10 specimens manufactured from the rods, not just one. All of the specimens are as identical as possible. Back in the lab, he has all specimens ready for use and picks out the first one. He mounts the specimen carefully and securely into the fatigue testing machine. Together with 2 half shells, he inserts one end of the specimen into the right specimen grip. With a union nut, he locks the right end of the specimen. Likewise, he mounts the left end of the specimen into the left specimen grip and tightens the nuts. The preparation is now complete. The material tester then selects the appropriate test parameters on the control computer. He intends to load the first specimen alternately with a tensile force of 7 kilonewtons and a compressive force of 7 kilonewtons. The mean force is 0. A click on the start button and the testing machine begins to stress the specimen periodically. Our fatigue testing machine is equipped with a mechanical resonance drive. The specimen is connected at its left grip via a load cell to the machine frame. At the right grip, a spring is mounted and there in turn a mass. An imbalance stimulates the mass to vibrate. Longitudinal guides prevent the mass from vibrating in the transverse direction. Via the spring, the test force acts on the specimen. By varying the excitation frequency of the imbalance, the test force can be controlled. In our case, the specimen is loaded with about 25 cycles per second. Meanwhile, the first specimen has already endured over 300,000 load cycles and still seems to be intact. In reality, however, several cracks have already developed starting from the surface, the so-called fatigue cracks. With each load cycle, they grow a bit further into the specimen. The biggest crack gains the upper hand, grows the fastest, and finally leads to fracture after 381,000 load cycles. The first test is finished. The material tester removes the fragments cautiously and inspects the fracture surfaces. At first glance, the fracture surface looks unimpressive. A closer look reveals two regions: the rather dull, predominantly flat fatigue crack propagation area and the rough residual fracture area. The residual fracture area results from the final catastrophic rupture. The fatigue crack propagation area has developed during the cyclic growth of the fatigue cracks starting at the surface of the specimen. What does the fatigue crack propagation area look like at higher magnification? One of the fragments is carefully placed on the specimen stage of our scanning electron microscope. Now we can investigate the fatigue crack propagation area in detail. In some places, but not everywhere, parallel grooves and ridges can be seen, the so-called fatigue striations. Each groove and each ridge has been formed by an individual load cycle, a typical phenomenon. Of course, now we want to know how many load cycles this material can endure with other loads. For this purpose, the material tester picks the next specimen from his supply and installs it into the fatigue testing machine. He chooses a higher alternating load for the second specimen, a tensile force of 7.5 kilonewtons and a compressive force of 7.5 kilonewtons. Under the increased load, the specimen is only able to withstand 43,600 cycles to failure. The third specimen is only tested with a cyclic load of 6.5 kilonewtons. Under this reduced load, it does not break even after 3 million load cycles. Additional specimens complete the series of measurements. Some of the specimens are tested with the same load we've already used. In this way, we get an impression of the range of scattering. To compare materials in a fair way, the different cyclic loads are converted to the respective stresses acting in the specimen. In this case, the stress alternates sinusoidally around the mean value, which is termed mean stress sigma m. In this series of tests, the mean stress is 0. The stress amplitude is labeled with the symbol sigma a. For graphical representation, the SN diagram is used, also termed Wöhler diagram. In an unusual manner, the predetermined variable is plotted upwards on the y-axis. It is the stress amplitude sigma a. And the result of the test, the number of cycles to failure n, is plotted to the right on the x-axis. To fit small and large numbers into the diagram, the x-axis is not scaled linearly, but logarithmically. The first specimen was loaded with 7 kilonewtons. This corresponds to a stress amplitude of 248 newtons per square millimeter. Under this stress amplitude, it broke after 381,000 load cycles. The second specimen was loaded with 7.5 kilonewtons. This corresponds to a stress amplitude of 265 newtons per square millimeter. Under this stress amplitude, it broke after 43,600 load cycles. And these are the results of the other specimens which have been tested by us. When additional specimens are tested and the results are displayed as a curve, it becomes clear that this material will not break below a certain level of stress amplitude, even after a very large number of cycles. This stress level is termed fatigue limit sigma capital A. For most steels with body-centered cubic structure, the fatigue limit is reached after 10 million load cycles at the latest. It must be noted that the experimental results scatter considerably. Therefore, instead of a sharp curve, a statistically defined scatter band is commonly used. Of course, most users don't load their components with a constant cyclic load, but rather in an irregular manner. Therefore, these components have to be tested under this type of loading, termed operational loading. In this test rig, critical bicycle components are loaded similarly to practical use. Stem and handlebar must endure the typical bending and torsional loads for a sufficient number of cycles. Only then they are approved for serial production. Moreover, the fatigue strength does not only depend on the material. The mean stress has an important influence, the shape, the surface quality, environmental conditions and much more. Not an easy story. Before an aircraft is allowed to take off for the first time, it has to go through extensive stress tests. The wings and many other elements are cyclically loaded in large test rigs. This later ensures the safe operation of the aircraft. Nevertheless, particularly important components are repeatedly examined for fatigue cracks in the course of operation. The tram, for instance, has to go into the test hall at regular intervals. Experienced staff use ultrasound to examine special components, especially the wheel set axles, to check whether they are still in perfect condition. Aircraft are also inspected for fatigue cracks at reasonable intervals. This helps us to depart for air travel without worry and land again safely.